Most people turn on a tap and never think about where that water comes from. They don't think about the treatment system that removed what shouldn't be there, the professionals who designed and installed the treatment equipment, or the regulation crafted to set a standard, a minimum standard to protect health and safety. They certainly didn't think about the 2 billion people worldwide who turn on a tap and get something they can't safely drink, or the countless others who don't even have taps to turn on. That gap between what most people assume and what is actually true about water is why the Drinkable podcast exists. I'm Greg Reinicke, Master Water Specialist and President of the Water Quality Association. I've spent 30 years working on water quality improvement across the United States, Africa, Asia, and the Middle East. I've seen what good water does for people and what bad water costs them. In every episode of Drinkable, we close that gap. We talk to the scientists, the engineers, the regulators, the dealers, and the people doing the real work of getting safe water to the people who need it. We do not fear, we do not hype, we just do water. This is Drinkable. Soft water kills water heaters. You've heard it. Heck, you might even have said it. I've heard it at supply house counters. I've heard it in online forums. I've heard it from well-meaning neighbors. I've even heard it from long-term plumbing professionals. Sometimes I've even heard it from water quality improvement professionals who should know better. This episode has a simple goal. I want to permanently retire the phrase over-softening from your vocabulary. And I want to give you a better explanation for something that has been misdiagnosed for decades, which is why anode rods fail faster in some homes than others. Grab a beverage. This one gets a little technical, but I promise it's worth the time. Let's start with what a sacrificial anode rod is actually doing inside the tank. Every steel water heater has microscopic defects in the glass lining, the weld seams, the fitting penetrations, spots where bare steel touches the water. Put an electrolyte in contact with two dissimilar points on the steel, and you get a galvanic cell. An anodic site giving up electrons, and a cathodic site consuming them. Left alone, that process eats the tank from the inside. So manufacturers then add a sacrificial metal anode that sits higher on the galvanic series than steel. That rod corrodes first, on purpose, so the tank doesn't. But here's the part that gets skipped over in the part store version of the story. The rate at which that rod sacrifices itself depends on three things: temperature, the electrochemical potential difference between the anode and the steel, and the electrical conductivity of the water itself acting as the electrolyte. That third variable is where the softener joins the party. Ion exchange softening is a straight substitution reaction. The resin grabs calcium and magnesium divalent ions and hands back sodium, a monovalent ion, to keep the water electrically neutral. One calcium ion in, roughly 2 calcium ions out into the softened water. More ions in solution means higher conductivity. In my experience, that increase averages somewhere around 10% after softening. So if your incoming TDS is 100 and you soften the water, we typically see that effluent outgoing TDS rise to about 110. Your mileage will vary with source water composition, of course. So yes, softened water is slightly more conductive. But no, that's not the villain of this story. Elevated conductivity from any source will accelerate anode consumption, and softening is only one of many ways water gets there, but it is a very minor increase in conductivity. Bradford White publishes generally solid technical guidance on this topic, and I want to credit them for that. One of their bulletins states plainly that in more conductive water, including softened water, the sacrificial process in magnesium anodes speeds up, and aluminum becomes the better material choice. I agree with that completely. Where I disagree is the next recommendation. In the same bulletin, they recommend targeting 10 to 12 grains per gallon of residual hardness rather than treating all the way down to less than 1 grain per gallon, on the theory that lower conductivity buys the anode more life. Respectfully, that's engineering around the wrong problem. The Water Quality Association's own technical position, and mine, speaking as someone who has 3 decades of practical and academic experience solving corrosion issues all over the world, is that hardness neither causes nor prevents tank corrosion. Water can either be soft or hard. It's not partially soft. 1 grain or less is soft. So the term under-softening, meaning we're blending back hardness back into the water, it's just less hard. It's still hard water. Not fully softening the water to squeeze another year out of an anode rod leaves scale-forming minerals in the system because you're not partially softening. You're just less hard. That less hard still forms scale. It reduces plumbing and appliance efficiency. It interferes with detergency. It interferes with body oils. It has such a huge interaction in a home, leaving hardness in the water in this crazy idea of trying to minimize corrosion. It's just silly. It's more about warranty posturing than defensible or logical corrosion control strategies. Conductivity-driven anode wear happens whenever the dissolved ionic load is high, no matter which ions are responsible and no matter where they originated from. And untreated hard water with 500 milligrams per liter of TDS comprised of calcium, magnesium, sulfates, bicarbonates, with 0 sodium in it will eat an anode faster than softened municipal water sitting at 250 milligrams per liter of TDS. It's just common sense. The WQA's Corrosion Education Kit, written by Doc Nolan and my good friend Joe Harrison, identifies high mineral concentration itself as the corrosion accelerator because it drives conductivity and current flow. That same document states, in plain English, ion exchange softening neither causes nor controls corrosion. Softening doesn't touch pH. It doesn't touch dissolved carbon dioxide. It doesn't touch dissolved oxygen, or even total ionic concentration, the factors that actually govern corrosion. It does change which cation is in solution. That's all. So now the elephant in the room, Langmuir. A lot of people lean on the Langmuir Saturation Index, LSI, way too hard. LSI tells you whether a natural water is likely to form or dissolve calcium carbonate scale. Softened water with the calcium stripped out, but the alkalinity retained, shifts negative on that index, which looks scary on paper. But you cannot equivalate LSI to softened water as though it behaves like naturally soft, naturally acidic water. The chemistry is not the same. Corrosion depends on too many interacting variables for any single index to describe it completely. LSI is just one data point, and it is not a reliable predictor of corrosion potential when dealing with ion exchange softening. Now let's talk about the 2 most common anodic materials and what goes wrong with each, because the symptoms show up in the field constantly and they frequently get misdiagnosed. Magnesium is the most reactive of the common anode materials, which makes it a very strong performer in normal conductivity waters, 100 to 300 TDS. And on those waters, they're typically good for 5 years or longer. In high conductivity waters, climbing above 300, field reports show complete depletion in as little as 6 months, all depending on how much total dissolved solids are in the water. Higher conductivity means faster anode depletion. When that anode is depleted, protection stops, and nobody in the house knows it happened because the tank gives them no visible warning until it leaks. Before it depletes, an overactive magnesium rod in highly conductive water can also, quote, overprotect the tank, generating excess hydrogen at the metal-water interface. That shows up as milky or cloudy hot water, spurting fixtures, and if there's any sulfate around for food, The unmistakable rotten egg smell that only shows up on the hot side, caused by desulfovibrio bacteria and others in the same family. Bradford White's Service Bulletin number 109 discusses this mechanism. There's also another issue that can be even more problematic. Excess cathodic current can blister or fracture the glass lining itself at the steel interface. Once that lining is compromised, the tank is exposed, no matter what you do with the anode. The second choice is aluminum. Aluminum is slower to deplete in conductive water, which is why manufacturers recommend switching on higher conductivity waters. But aluminum brings its own baggage. In waters where the pH is above 8 or below 6.5, aluminum solubility climbs and the rod sheds aluminum hydroxide. It's that tapioca jelly-like precipitate that clogs aerators, gets hung up in washing machines, fouls filter cartridges, and makes water cloudy. A.O. Smith has a pretty good write-up of this in Tech Bulletin 14, although I don't quite agree with every single thing they say in there. There's also a microbial angle worth knowing about. A 2023 Virginia Tech metagenomics study found aluminum anodes connected with the enrichment of Mycobacterium avium, an opportunistic pathogen in hot water plumbing, more so than with magnesium or powered titanium anodes, suggesting that aluminum is food for the metabolic process of these bacteria. I don't like that. If sacrificial anodes deplete, dump metal into your water, demand an inspection schedule most owners will never keep, and still produce these failure symptoms, then the fix is an anode that needs none of that. We call that impressed current cathodic protection, ICCP. That process has protected pipelines, ship hulls, and industrial tanks for decades, and it translates directly to the residential water heater market. Instead of relying on a passive galvanic reaction, a small external power supply drives current through an inert titanium electrode coated with a mixed metal oxide. This makes the entire tank interior the cathode. Steel at the cathodic potential does not corrode, and of course the titanium electrode barely dissolves. It will typically outlast all of us. The part I find beautifully elegant is the automatic voltage adjustment. Ohm's law, voltage equals current times resistance, governs that electrochemical circuit just like all circuits. When conductivity is high, resistance is low. The unit needs less voltage to hold its target current. When conductivity drops, resistance of the water rises, and the unit pushes more voltage to compensate. A properly designed constant current supply does this automatically, continuously, and without any human interaction. If anything changes on the TDS of the water, the current automatically adjusts. Just like that. This helps to prevent overprotection, the formation of hydrogen bubbles, because you never exceed the design threshold. You don't have that feedback loop with a metallic sacrificial anode. That metallic sacrificial anode just pushes whatever current the galvanic potential allows, whether it's needed or not. If you're a plumber or water quality improvement technician listening to this, here are some practical tips. First, always test the water. Hardness, TDS, conductivity, pH, alkalinity, always at a minimum. Understand what you're looking at before you recommend anything. And it's okay not to know all the answers. It's okay not to understand all the chemistry. That's why you have people on your team in your own company, with your equipment supplier, or even with the Water Quality Association that you can lean on to back you up. We're all learning. Don't ever feel inadequate because you don't know all the chemistry all the time. After you've tested the water and you understand what you're dealing with, I seriously recommend electric anodes as the default on any installation where I'm seeing an elevated TDS. In my companies, if I see more than 500 TDS, we're putting an electric anode in no matter what. And if I see a potential where the TDS is lower today and I anticipate it might get higher in the future, electric anode, no matter what. It's a one-time decision that removes an entire category of potential complications and future callbacks. If you're going to install a sacrificial metallic anode instead, match the material to the water and then set a defined inspection schedule. Annually on TDSs above 300, every 2 to 3 years on lower conductivities. Replace it when you see more than 6 inches of exposed core wire or a diameter that's reduced below half the original. Or just go back to the electric anode and don't mess with the silly metallic one. Now, the big one. Get your softener programming right. A properly operating ion exchange water softener does not make water salty. If you ever have salty water reported in a home, that water softener is not working correctly. It is not normal to put salt into water. So make sure your rinse cycles are set. Make sure your salt dosage is set correctly. Make sure your regeneration frequency is set correctly. All of this matters. We don't want to waste salt. We don't want to waste water. We want to make sure we're providing the client with the most softening benefits for the very lowest impact on their budget and the environment. And don't try to listen to the advice that 10 to 12 grains per gallon of residual hardness is a good target to protect a water heater. Soften to less than a grain. Then solve your corrosion protection issue as a completely separate thing. And one more thing. Tell every customer every time not to drink or cook with hot water straight from the tank. That advice stands regardless of what kind of anode you're using or what kind of water treatment system you have. Hot water pulls metals out of plumbing faster than cold water does. It accelerates all chemical interactions. And whatever's at the bottom of that tank, whether it's sediment, oxidized anode byproducts, bacteria, that's going to end up in the hot water at some point. Now, it's less of a threat in modern tankless and indirect systems where the tank components are typically stainless and we don't have anodes, but you still have a potential for leaching metals from faucets and fixtures and even volatile organic compounds from the PEX pipe itself at higher temperatures. Just don't drink from the hot. Certified water specialists and master water specialists are trained to look at the whole chemistry picture, not just a hardness number on a test strip. They understand how softening interacts with corrosivity, how TDS drives galvanic behavior, how anode material choice affects downstream water quality, and how to specify the right protection strategy for the water that's actually in front of them. That is the entire premise behind WQA certification. Complex water problems get solved by certified people using certified products, not by folklore repeated at the counter. This is also, frankly, a trust conversation. If you sold the softener and you never mentioned the anode, and that water heater rusts out in 3 or 4 years, you own that conversation in the customer's mind, whether it's fair or not. Bring it up first. Do the right thing. So let's put the myth to bed. Softened water is not uniquely corrosive or dangerous to your water heater, or anything else for that matter. Elevated conductivity from any source speeds up anode consumption, and softening is just one minor contributor among several contributors to elevated conductivity. The manufacturer workaround of trying to use hard water to protect an anode trades real water quality for an unproven benefit. Long-term fix is impressed current cathodic protection, specified once, automatically adapting, and takes an entire category of failure right off the table. That's all for this episode of Drinkable. If today's conversation raised questions about your own water quality, the best place to start is with a WQA certified professional. Certification is not a marketing term. It means that the person sitting across from you has been tested and vetted and is held to a defined standard of knowledge and ethics. You can find a certified professional at find.wqa.org. And if you want to go deeper on the science, the regulations, or the industry, I write long form at gregknowswater.com and on Substack. Links are in the show notes. If Drinkable is useful to you, share it with someone who needs it. Subscribe wherever you get your podcasts, and leave a review if you're willing. It helps more people to find the show. I'm Greg Reinicke. What a great time to be in the water business.